thanks to Associate Professor Maria Carmen's Figueroa Bonza for the nice overview introduction. Now I would like to introduce more details about my PhD thesis. So the topic is ontology-driven data access and data integration with application in the materials design domain. I'm supervised by Professor Patrick Lambrix, and please allow me to make a small correction. I'm also co-supervised by 3 co-supervisors. So Professor Nahid Shahmari and Associate Professor Ricardo Amento and Associate Professor Olaf Khatib. So now I can introduce more details. Okay, so I will follow this agenda to present. First, I will introduce some research background, motivation, and how we formulate the research problems. Then I will introduce the contributions of my thesis, as well as some limitations and interesting directions for future work. Finally, I will conclude my presentation. So in general, my thesis is motivated by issues that relate to both material science domain and semantic web field. And my thesis contributes to both the fields. Before I move on to detailed motivations, let me introduce some research background. So, materials design is regarding designing materials with specific materials properties. Such properties may refer to, for instance, toxicity of the strength of materials. Different chemical elements and different structures of materials also influence these properties. Thus, there is immense space to discover potentially useful materials. For example, there are many billions of possible combinations up to just 6 different chemical elements. Traditionally, researchers can explore materials by experiments, but for some extreme conditions such as ultra-high temperature and ultra-high pressure, experiments cannot be easily conducted. By the development of a materials modeling method, people can do material simulations by computer programs, and such computer programs can generate reliable materials data. Materials calculations run such computer programs. The many software programs can achieve materials calculations and generate reliable materials data. At the same time, quite a lot of databases have emerged in recent decades. The researchers in the domain can not only upload their data to these databases, but they can also download the data and use the data in their data-driven workflows. For example, in this slide, I show 3 well-known databases. They are the Materials Project, OQMD, the Open Quantum Materials Database, and NOMAD, Novel Materials Discovery. These databases commonly share data via web APIs, such as REST API. In materials design, the users usually use the data from these databases for data-driven workflow. But there are some problems that, for instance, one user needs to search materials from different databases. These databases are usually heterogeneous in nature. For example, if a user wants to search a material with the composition gallium nitride from these 3 databases, the result is slightly different from these 3 databases. For example, they all have a column to represent the chemical composition, but they either have different name of the columns or different insights. For example, both Materials Project and NOMAD have a column formula to represent the chemical composition. But in Materials Project, the formula column represents the reduced chemical formula, which is the simplest form of ratio of different chemical elements. But for NOMAD, the formula column represents the unit cell formula, which is different from reduced chemical formula. At the same time, we have OQMD, which contains a column composition to represent the reduced chemical formula. So the researchers in the domain realized that such differences may bring problems when we need to integrate and access data from multiple databases. Therefore, there is an ongoing effort which is OPMAT, Open Databases Integration for Materials Design, which aims to design a common API to make materials databases interoperational. So we see that semantics are needed for the domain. We can use ontologies to represent the semantics. Ontologies can help in standardizing terminologies. Ontology can also help in accessing, integrating data with semantics aware. At the same time, ontologies can also help in making data fair, which is short for fungibility, accessibility, interoperability, and reusability. So now let me introduce the detailed motivations of my thesis. So for materials design domain, we see the need for a semantics-aware and integrated way for querying data among heterogeneous data sources. We can use ontology-driven approaches, but before doing that, we also need to develop domain ontologies, since at the moment we started the work, there is no such domain ontologies. So ontology-driven approaches can play a role in data access and data integration over heterogeneous data sources. There are still challenges. For example, traditional ontology-based data access systems, they focus on data in relational model, which can be viewed, stored in a relational database. But the data can be modeled in different ways, shared and queried in different ways. For example, tabular data via SQL queries, or JSON formatted data via API requests. We see that GraphQL can be used in ontology-driven approach since GraphQL can produce an integrated view over underlying data. But there do not exist formal methods for constructing a GraphQL server for semantic and integrated data access. Therefore, we formulate our research problems. So, given underlying data modeled in different ways, shared and queried in different ways, the goal of my thesis is to answer the question how to provide semantics-aware data access and data integration over such heterogeneous data. Furthermore, we specify this problem into 3 sub-questions. The first question relates to how to use GraphQL for semantics-aware data access and data integration. The second question relates to how to leverage ontologies to generate GraphQL APIs to avoid manually constructing concrete details of GraphQL servers. The last question relates to how to extend domain ontologies by mining unstructured text with validation from domain experts. Now let me introduce the detailed contributions of my thesis. To answer the first research question, we outline a GraphQL-based framework for data access and data integration. This framework is a general framework which can be used for different domains for data access and data integration. So what is GraphQL? GraphQL is a conceptual framework for building web APIs. The framework introduces the notion of GraphQL schema, which describes how underlying data can be accessed. The framework also contains resolver function implementations that are responsible for accessing underlying data sources, combining and structuring returned data according to the GraphQL schema. At the same time, the framework contains a graph query language, which allows users to write GraphQL queries. Now let me introduce some details about GraphQL. So GraphQL schema basically defines types, the fields of the text and the value types of the fields. And object type are common type definition in GraphQL schema. For example, in this schema, we have the object type university, which has 2 field definitions. The first one is university ID field, of which the return type is string. The second field definition is departments field, of which the return type is a list of departments. Department is also an object type definition in this schema. So in this way, we build the connection between different objects, between different object type in GraphQL schema. GraphQL schema also allows to define abstract types, such as interface type. So in this example, we have author interface, of which the author interface has a field author ID of which the return type is a string. At the same time, we have a professor object type definition. The type implements author interface, and it must have the same author ID field definition. GraphQL schema presumes a query type to represent query operations. And the query type is similar as an object type. It has different field definitions. And each field definition is corresponding to a kind of queries. For example, in this query type, we have the university list field, of which the return type is a list of universities. So according to this field, we can write the GraphQL query to request all the university entities from underlying data sources. As I mentioned before, resolver function implementations is a building block for GraphQL server. So we can write a resolver function according to this university list field to access underlying data source and request all the university entities. Meanwhile, GraphQL schema also allows to define input types, which can configure the behavior of fields. For example, in this schema, we have an input type for the university list field. We can use the input type to represent filter expressions. And in this query example, we use the input type to represent a filter expression university ID equals to U1. So this GraphQL-based framework contains two basic processes. The first process is GraphQL server generation process, in which the users or developers of GraphQL servers define the ontology semantic mappings, which will be used to generate the GraphQL servers. And the ontology plays a role of integrated view of underlying data. Therefore, the generated GraphQL schema also becomes an integrated view of underlying data. After this process, the GraphQL server can be set up. This process does not need to be repeated unless the ontology and the semantic mappings change. The second process is the normal GraphQL query answering process. A GraphQL query will be validated against the GraphQL schema. Then the resolver function is responsible for accessing the underlying data sources, then combining and structuring the returned data according to the GraphQL schema. Finally, the query result will be returned to the users. So the next question comes, why we use GraphQL in the data integration system. So from theoretical point of view, GraphQL schema can help to provide a unified view of data from multiple heterogeneous data sources. And the GraphQL resolver functions can be implemented without restrictions of underlying data sources. From practical point of view, GraphQL has self-documenting specification, so users can find the schema easily. Then, since there are no formal methods to employ GraphQL for semantics aware data access and data integration, we further investigated how to leverage ontologies to generate GraphQL APIs to avoid manually constructing concrete details of GraphQL servers. So to answer this question, we implement a prototype of the framework, which is ontology-based GraphQL server generation, OBGJ. Specifically, we contribute in two directions. The first contribution is ontology-based GraphQL schema generation, and the second one is a generic GraphQL resolver function. So to generate GraphQL schemas based on ontologies, we take an ontology represented as description logic T-box as an input. A T-box contains concepts and relationships among concepts, as well as relationships between concepts and literals. For example, suppose we have a small ontology to represent the university domain. We have concepts such as university and department, as well as we have the relationship between these two concepts. Then in the T-box, we will have such two concept inclusions that relate to university concept. This one says all the university entities are entities that have departments relationships, while each department's relationship connects to a department. Therefore, in the graphical schema, we can define a university object type and a field departments, of which the return type is a list of departments. So in this way, we reflect the semantics from a T-box in a graphical schema. In a data integration system, we usually need a global schema to represent the integrated view of underlying data, since underlying data usually follow their local schemas. And we usually need semantic mappings to define the mappings between queries over the global schema and the queries over local schema. In ontology-driven approaches, we usually, such semantic mappings can transform underlying data into RDF formatted data, which contains tuples in the format of subject, predicate, and object. ML is one of the languages to define semantic mappings. In such semantic mappings, we can define what kind of the data sources and how we can access the underlying data sources. And there are detailed definitions about how to generate the subjects, predicates, and objects. Remind in my previous example, we have the resolver function corresponding to university list in the query type. So in that way, we need to define multiple resolver functions corresponding to different fields in the query type. But now, since we use the ontology to generate the graphical schema and we use the ontology to get the definition of the semantic mappings, we can use the semantic mappings to just implement one generic resolver function. And this generic resolver function is responsible for example, passing the semantic mappings, then accessing the underlying data sources, combining and structuring the returned data according to the semantic mappings. So in this framework, the ontology plays an important role in driving the generation of the graphical server. So before we move on to the evaluation and application of this framework, let me first introduce what we do for our targeting domain materials design. So basically, we developed a domain ontology, which is materials design ontology, MDO. The development of MDO follows some relevant scenarios from NION methodology, such as requirements analysis and reusing concepts from existing ontologies. The requirements analysis is to specify use cases, computation questions, and additional restrictions that the ontology should satisfy. MDO reuses concepts from some good practice in other ontologies, such as the provenance ontology and the unit-related ontology QUDT. We also looked at domain ontologies in physics and chemistry. For example, we reuse some concepts from Chebby and Amo. MDO was developed in modules, which allows easy extendability. During the development, we discussed with the domain expert to decide what concepts, relationships, and axioms that MDO should cover. In this figure, I show the concepts and the relationships of MDO. In the middle of the figure, we have the core module, which contains concepts such as structure and property. Property has two sub-concepts, which are calculated property and physical property. The core module is reused by other modules. For instance, we have the structure module, which is used to model the structural information of materials. Then we have the calculation module, which models some relevant concepts related to computational methods. So in this part, I show the concepts that we reuse from the provenance ontology. We mainly reuse the software agent concept to build the connection between calculation and software agent to state which software produced the calculation data. And we also have the connection between reference agent and the structure to state which reference, usually a paper, published the structured data. In this part, I show the concepts and the relationships that we reused from other ontologies, such as item from Chebby and material from MO. So, since in a data integration system, sometimes the ontology and the ontology may need to be enlarged if we have new databases or new kinds of data to be added in the existing databases. Therefore, it is valuable to investigate how to extend the domain ontologies. So in this work, we propose an approach for ontology extension. And use the approach, we extend ontologies in the nanotechnology domain and our materials design ontology. So basically, this approach is based on phrase-based topic modeling, formal topical concept analysis, and domain expert validation. So we apply the phrase-based topic model over unstructured text. After the topic modeling, we will have a number of topics, while each topic is represented by a number of phrases. Then we apply the formal concept analysis over the result of topic model. Our approach is a semi-automatic method, where we have a domain expert to give validations of the result. So formal concept analysis is based on mathematical order theory. So by defining formal concepts, we can derive the relationships between formal concepts. For example, in this slide, we have topic 3 represented by phrases 1, 2, and 3. And topic 2 represented by phrases 2 and 3. We say that topic 3 is more specific than topic 2. So in this way, we can derive the hierarchy among different formal concepts. And our domain expert give validations in 2 directions. The first one is to interpret all phrases appearing in topics, and the second to interpret topics. So in the validation part, we aim to identify what are the existing knowledge in the ontology and what are the new knowledge should be added into the ontology. For example, we may ask the domain expert, does a phrase exist in the ontology already, or should a phrase be added into the ontology? Using this approach, we extend 2 ontologies in the nanotechnology domain, which are nanoparticle ontology and e-nanomapper ontology. We collect unstructured text from publications that gathered by the nanoparticle information library. And then we also compare our approach with another ontology learning system, text-to-onto. So based on the result, we found that there was some new knowledge that are discovered by our approach, but text-to-onto does not. At the same time, there were also some results that produced by text-to-onto, but our approach does not. So in some way, we can see that the 2 approaches are complementary. Then we use this approach to extend our materials design ontology. So different from the nanotechnology domain, where we have the nanoparticle information library that gathers all the relevant publications, for materials design, we don't have such database. Therefore, we make some extra efforts to generate more precise results for domain expert validation. For example, we add a pre-process step for the topic model, and we also add a number of parameters to select more frequent phrases before the topic modeling. In one of the experiments, we have 88 candidate concepts, and some of them are very relevant to the calculation module in our MPO. For example, we have the candidate concept projector augmented wave method concept. And the domain expert also validated the topics. And we have, for example, in the same experiment, we have 9 relevant topics out of 10. And some topics are relevant to the calculation module and structure module of our MDO. So now with the help of MDO and our prototype of the ontology-based GraphQL server generation, we can evaluate our framework and apply it in our targeting domain. So first, we focus on a real case evaluation. We collect data from two databases from the domain, which are Materials Project and OpenMD. And by using our prototype, we generate two variants of our system. The first one is OBGGN-RDB that deals data in relational databases, and the second one is OBGGN-Mix that deals data in different formats, such as CSV files or JSON files. We use MDO to define the semantic mappings, and we compare our two systems with three other systems. One is MorphRDB, which is a state-of-the-art ontology-based data access system. And we also compare our system with HyperGraphQL and UltraGraphQL. We created queries that cover different features, such as domain interest, the result sets of queries, and different filter expressions. We compare query execution time on different queries of different systems over different sets of data sets. In general, in the result, we found that for queries without filter conditions, all the systems have increases of query execution time when the data set increases. But MorphRDB is less sensitive. And we also found that our OBGGN-RDB can outperform MorphRDB for some queries in smaller datasets. And for some other queries, they have close query execution times. Meanwhile, for queries with filter conditions, we mainly focus on comparing our OBGGN-RDB and MorphRDB. And we found that these two systems have stable or slightly increased query execution times for those queries that have constant result sets or simple filter expressions. So such queries, such filter expressions can be easily rewritten in SQL queries that can be evaluated against the relational databases. But in general, the differences of query execution times between these two systems are less than those for queries without filter conditions. Then we apply our framework for materials design domain, and we focus on using MDO to annotate the response from Optimate API, as well as we focus on comparing the GraphQL API in which the server is generated by our prototype with the general Optimate API. So when annotating the response following Optimate API, we found that for some fields, we cannot use MDO to annotate, but they can be easily implemented in the future if we model more data properties associated with the structure concept in our MDO. By comparing the GraphQL API and Optimate API, the main result is for GraphQL API, the user can easily specify what returned field they want in the final result. Now let me introduce some limitations and interesting directions for future work. So the first direction relates to user-friendly data access, data integration, and ontology extension. So in a data integration system, sometimes the ontologies and mappings may need to be modified. Based on our current study, there were no methods that focus on providing users with suitable tools for such maintenance. The second direction relates to that we can foresee when material science domain employ more semantic web-based technologies, there could be some problems. For example, different research groups in material science are developing ontologies. These ontologies may share some common concepts or relationships. At some point, we may need to align these ontologies. But for the domain, we don't have any knowledge bases or theories that can be used for an ontology alignment system. So therefore, it is valuable to investigate in the future how to construct such knowledge bases or theories. So far I have introduced the motivations and detailed contributions of my thesis. Now let me conclude my presentation. So given the underlying data modeled in different ways, shared and queried in different ways, the goal of my thesis is to answer the question how to provide semantics-aware data access and data integration over such heterogeneous data sources. To solve this problem, we first outline a GraphQL-based framework for data access and data integration. Then this framework is a general framework that can be used for different domains for data access and data integration. Then we investigated how to leverage ontologies to generate GraphQL servers. So we don't need to construct concrete details of GraphQL servers. Then we implement a prototype, which is ontology-based GraphQL server generation, OBGJ. Then we focus on our targeting domain materials design, and we developed a materials domain ontology, which is MDO. With the help of MDO and OBGJ, we evaluate our framework and apply the framework in the domain effort optimized. Then in another direction, we looked at how to extend domain ontologies based on topic modeling, formal concept analysis, and domain expert validation. Using this approach, we extend two ontologies in the nanotechnology domain and our materials design ontology. So in conclusion, our approach can alleviate the heterogeneity over different data sources and provide semantics-aware data access and data integration to the users. So the users can have a unified and integrated view of underlying data. And this is my last slide. Thanks for your attention.